Welcome to the first of several videos on the applications of first-order differential equations. This video will focus on exponential growth. The differential equation dp dt equals k times p, or p prime of t equals k times p of t, models exponential growth, which means the rate of growth is proportional to the population or amount. So looking at these again, this is telling us the change of p with respect to t is equal to some constant k times p, or the derivative is equal to a constant times the original function p of t. And this can also be used to model continuous interest. While we will solve this differential equation by find p of t, the only function that satisfies this differential equation is p of t equals p sub 0 times e raised to the power of kt. We should recognize this exponential function from our algebra class, where p sub 0 is the initial amount, k is the growth rate, and t is the time. But let's start by looking at an example. A population of a small town grows proportional to its current population. The initial population is 5,000 and grows 4% per year. This can be modeled by the differential equation dp dt equals 0.04 times p, and p of 0 is equal to 5,000. We want to find an equation to model the population, determine the population after 3 years, then determine how long it will take for the population to double. So to find the equation to model the population, we're going to solve this differential equation. So if we write this in differential form, we would have dp is equal to 0.04 p dt. We want the p on the left side of the equation, so we're going to multiply both sides by 1 over p. So we'd have 1 over p dp is equal to 0.04 dt. Now we can integrate both sides of this equation. The antiderivative of 1 over p would be natural log absolute value of p, but we know p has to be positive because it's the population. So we have the natural log of p. We'll put the constant of integration on the right side. So this is going to be equal to the antiderivative of 0.04 with respect to t would be 0.04t plus the constant of integration. Now once we have this equation, if this is true, then e raised to the power of natural log p must also equal e raised to the power of this sum. By doing this, the left side simplifies very nicely to p, which we know is going to be a function of t, so we'll write p of t equals, now because we have a sum here, this would be e to the 0.04t times e to the c, but e to the c is just a constant, so let's let e to the power of c equal p sub 0. So now we have an exponential function that would satisfy this differential equation. It's going to be p of t equals p sub 0 times e raised to the power of 0.04t, which does fit the form of the exponential function that we discussed on the previous slide, also given here. But now let's go ahead and verify that p sub 0 would actually be 5,000. So p of 0 would be equal to times e to the 0 power, which again we know must equal 5,000. Well, e to the 0 is equal to 1, so we do have p sub 0 equals 5,000. Giving us our particular solution to the differential equation, we have p of t is equal to 5,000 times e raised to the power of 0.04 t. Again, which matches the exponential function that we knew would be our solution given here. Now let's go ahead and use this function to answer a couple questions. We want the population after 3 years, so we're just going to substitute 3 for t. We need a calculator for this part. So 5,000 times e raised to the power of 0.04 times 3. So the population will be approximately, we'll round to the nearest person, so we're going to round down, 5,637 people. The last question asks us to determine how long it will take for the population to double. So again, starting with our population function, the initial population is 5,000. 5,000 times 2 is 10,000. So we're going to set P of t equal to 10,000 and solve for t. Divide both sides by 5,000. This would be 1. 10,000 divided by 5,000 is 2. This will always be 2 when trying to find the doubling time. And to solve for t, we'll have to use the properties of logarithms. We'll take the natural log of both sides of the equation. So on the left side we have natural log 2 equals, here we can apply the power property of logarithms. We can take this exponent here and move it to the front. So we have 0.04t times natural log e, but natural log e is equal to 1, so that simplifies out. So now we just divide by 0.04. And go to our calculator to find the approximate doubling time. So we have natural log 2 divided by 0.04, which happens to be our growth rate. So the doubling time is approximately, let's say, 17.3 years. I do want to point out there's a shortcut for determining doubling time. Let's call it capital T. The doubling time is always going to be equal to natural log 2 divided by the growth rate, we'll call k. Okay, I think we're short on time, so we'll go ahead and take a look at the second example in part 2. I hope you found this helpful.